Okay, so here's a question. Ready? So a ball. This is in your book. A ball rolls 16 feet in 4 seconds. So versus something like it rolls 16 feet in 4 seconds. On average, how fast did it roll?
4 feet per second.
4 feet per second. So what did you do there?
Just did 16 divided by 4.
Yeah. Change in distance divided by change in time, right? So they actually did some subtraction for you already by measuring where it started, measuring where it ended, and subtracting and saying the difference is 16 feet, and then measuring the time using a clock when it started, and measuring the time when it stopped using a clock to find the difference of 4 seconds. Okay? How fast was the ball moving at second 3? So at second 3, in that second, how far did it go?
It went 12 feet.
Over the course of that second.
Oh, over the course of a
4
second.
feet a second. It went 4 feet.
So at that moment, ready? So like if we have video, right? And we're watching the milliseconds tick off, right? And then boop, boop. And at second 3, we stop it. Or at that very moment, how fast is it going? Do we have math that allows us to figure that out?
Yes.
No.
Oh.
Okay, no. Not currently. We will in a moment. Okay? So the point is, like, if I subtract, if I say from second 3 to second 3, how fast is it going? Well, the change in x in time is 0. I can't divide by 0. Right? So how am I going to do this? So that's what you see on page 737. They walk you through that. And they say V average equals delta S over delta T equals 16 feet over 4 seconds equals 4 feet per second. Then below that it says delta average, AVE, I think is what they're talking about, equals delta S over delta T. At second 3, it's 0 feet over 0 seconds. We can't do anything with that, right? So we're going to deal with these. We're going to start to deal with a limit here, okay? So check it out. Okay? Example 2 at the bottom of 737 says this. A ball rolls down a ramp so that its distance s from the top of the ramp after t seconds is exactly t squared feet. Okay? So what we're saying is d of t equals t squared. Right? That's what it says?
Yes.
Yeah. Yeah, t seconds. Okay? So we want to know what the velocity is at 3 seconds. Okay? So check this out. Let's say so we have this is t squared, right? So I'm out of the frame for David now. That's okay. That's the bonus of being present. So it looks like this. 1, 2, 3, 4. And then 3, 9 would be here. Okay. So this is distance as a function of time. Okay. So what we're looking for is the rate of change, boom, right there. Okay. Now, typically we can only find the rate of change over a span if it's not a line. So we can find an average rate of change between 2 points. So let's begin by doing that. So let's say from 3 to 3.1, what was the average rate of change? And so notice what we're going to do is we're going to make a line. If we made a line, this is a curve. If we made a line that would not go along that curve, in fact, it would be inside that curve, right? From x equals 3 to x equals 3.1, the slope of that line would be the average rate of change over that 0.1 second, right? Yes? Yes? Okay, so in order to find our average rate of change on the interval 3 to 3.1, we would go, all right, f of 3.1 minus f of 3 over 3.1 minus 3. Change in y over change in x. Okay? So 3.1 squared is, use your calculator.
9.61.
9.61 minus 9 over 3.1 minus 3 equals 0.61 over 0.1 equals 6.1 feet per second. Okay? So that means during that time, from 3 to 3.1, all right, it was going 6.1 feet per second. So it's accelerating as it goes down a ramp. Is that what we expect?
Yes.
Oh, sorry, I could have said that in the next step. But we expect it to start going faster as it goes down. That's why it's not a constant velocity, which we'll see here. Look, from f of, what do they do next, 3.05? Yeah, 3.05 minus f of 3 over 3.05 minus 3. So what's this numerator? Give me the two terms, or that 3.05 squared.
Uh, 9.3025.
Minus 9 over 3.05 minus 3. Now I might need your help on this as well. 0.3025 over 0.05. What's that?
Uh, 6.05.
6.05 feet per second. So consider, okay? Is that slower or faster than the one before it? Slower. So, and again, that's what we expect, because this time span from 3 to 3.1 is further along the journey of the ball than this time span of 3 to 3.05. So in that, notice this is half of the time as this, right? This is the first half of that interval. So what would you expect to see if we saw the speed from 3.05 to 3.1? It would be faster than this, actually, because this brought it down, right? So it's changing more rapidly in that time. So the ball's accelerating as it goes down. So if you had to make a conjecture now, okay, let's just do it. Okay, let's just do it. Let me just show you. So we could keep doing smaller and smaller intervals. We could go 3.005, 3.0005, and so on. And we could keep getting numbers, and they would approach something. Okay? A limit or an asymptote if we were graphing this. Okay? And notice, like, we could write this as a graph by having that d, that delta, between the x's be our input, and write it out, right? Okay, so if we just had, like, 3 plus x squared minus 3 squared over 3 plus x minus 3, which is just x, okay? Which is actually what we're going to do here. So check this out. So here's what we want to find, okay? Consider, these are some time t, okay? These right here are some time t. So let's write an expression for this that generalizes to any t. Rather than continuing to plug in various t's, let's just see the shape of what happens if I plug in t there. So this is down below, okay? So if I say, watch this, I'll write it as f of t, or no, okay, so I'll go ahead and use t squared. So t squared minus 3 squared over t minus 3. Okay? Now, and that's the rate of change. This is the rate of change between 3 and time t. But remember, what did I really set out to look for?
Speed at that specific.
Yes. So we call this the instantaneous rate of change. So the instantaneous rate of change at 3, right? So really, I want to be able to say, I want to be able to put 3 in here. And that was what caused our problem originally, is we would create 0 over 0, right? So what we're trying to do is avoid having a 0 here, but still figure out what's happening when t equals 3, okay? So, and this is kind of ancillary, related. Anybody remember what happens on a graph when the algebraic expression divides by 0? So algebraically, in the equation, if I end up with a 0 in the denominator, what happens graphically?
Is it undefined?
Yeah, meaning it has a what?
Asymptote.
Or a
The other one.
hole
Oh yeah.
or a jump. So typically this would be an asymptote in most cases, what we're about to deal with. So this is the change in they said S. I don't know why they said S. Mine's D, so I'm going to use D. Okay, in the book they used S. I don't know why. Change in D over change in T. This triangle is a Greek delta. Okay, so it's a Greek delta and means change. Delta means change. And now I want to find this. I want to find the limit of that expression as t goes to 3. So this is, remember, what's happening in a graph of when I approach an asymptote or a hole is it looks like it's going toward a certain value, it just never actually gets there. And it never actually gets there in this case because I would divide by 0, but I'm going to say, yeah, well, what does it look like it's doing? Okay. So we would say, all right. Well, this is a difference of squares. Okay. So how does a squared minus b squared factor? What's a difference of squares? How do you factor a difference of squares? You remember?
I completely forget this.
A plus b, a minus b? Would that work?
Yes.
How do you know?
Because now that you said that, it
cancels
cancels
out.
out.
It's plus and minus.
Boom, because the a, b terms cancel out. Right? So it's a first times first, a times a. Outers, a times negative b. Inners, a times positive b. Lasts, negative b squared. So the plus ab, the minus ab, they cancel. I'm left with a squared minus b squared. So this goes to t plus 3, t minus 3, over t minus 3. So again, I'm not actually plugging in 3, but I'm imagining what happens as I get very close to plugging in 3. So because I'm not actually plugging in 3, I can cancel these, because I can divide by something that's not 0, which it won't be 0 as long as t is not 3. So cancel, so it equals t plus 3. So now I just plug in 3, and I get what? I plug in 3 for t? 6. So really we're saying the graph of this, okay, will look like 6 as I get very, very close to 3 for t. So this being the formula for the rate of change between 3 and some future time, okay, as t approaches 3 in that graph, we're going to get very close to 6. Okay? So we would say the instantaneous rate of change at 3 is 6 for this. Cool? So the premise is, again, I'm basically finding the slope. So that means that if we're going to do this next, so I'll say that. We're basically finding the slope. Previously we couldn't find the slope of a curve, okay, unless we just picked 2 specific points. Now we know how to find the slope of a curve at a point, okay, at a point. Okay? And it's by using a limit so that technically we're not plugging in 3, but we're saying as we get closer to 3, y will get closer to 6. Okay?
Yeah.
All right. So that means that at that very instant, the ball was rolling 6 feet per second. So this gets very handy in physics, particularly when we extrapolate it another time, which is then we can measure the acceleration at a given moment, and yada, yada, yada.
Sounds like a lot of physics stuff. It's
Okay. Yeah, so that's where they're saying on page 738 in the green and blue box. Definition, informal limit at A, is when we write limit as x approaches A of f of x equals L, we mean that f of x gets arbitrarily close to L as x gets arbitrarily close but not equal to A. So it's crucial that we're saying x doesn't ever actually equal A, because then I'd be dividing by 0 and I can't do that. What we're saying is it's getting arbitrarily close to A, meaning the difference between x and A is so negligible I can forget about it. And at that point, f of x gets arbitrarily close to L. So if we're saying the limit as x approaches A of f of x equals L, some limit L, which in that case 6, okay, we're saying that f of x gets so close to 6, the difference is not worth talking about, as x gets so close to A that the difference is not worth talking about. That's the thing about arbitrarily. Okay? I think. Or they just mean close, relatively close. But, yeah. Okay? So, so recall, all right, I'm going to try to blow this up. Okay? So we've been doing this. Okay? Like if I find the average rate of change between these 2 points, I would say that average rate of change is the slope of that line, right? Yes? Now I'm finding the instantaneous rate of change right here. So that's the slope of what line? Yes. So imagine I'm getting these 2 points closer and closer together. This line would move more and more out this way, right? Toward the outside of the curve, until finally I just have boom, 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 boom. Imagine it's actually a little closer than that. What's it called when a line touches a single point on a curve? What's that line called?
Is it the tangent?
Tangent. So this is a tangent. This line is tangent to the curve at x, at that value of x. Okay? So if right here, if this is x, then this line is tangent to the curve at x. Okay? So, for instance, example 3 on page 739 says, use limits to find the slope of the tangent line to the graph of s equals t squared at the point 1, 1. Okay? At the point 1, 1. So again, we're going to go, we need to first find the slope. Limits as t approaches 1 of t squared minus 1 squared over t minus 1. Right, we want to find that. Okay. So now again we go t plus 1, t minus 1 over t minus 1. Cancel. This equals t plus 1. So the limit as t approaches 1 of this is 2. So my notation was bad. Sorry. And I think it was on that last one too. So I would say the limit as t approaches 1 of t plus 1, t minus 1 over t minus 1 equals the limit as t approaches 1 of t plus 1, which equals, now I would say, the limit as t approaches 1 of t plus 1, what am I getting very, very close to? 2. So 2 is the limit as t approaches 1 of this expression. Okay? So now we say that the slope of the line tangent to s equals t squared at the point 1, 1 is 2. Okay? Yes?
Yes.
So I want to point something out. I use examples where they've been worked out in the book already, and I work them on the board. And I know that's probably why you guys don't write them down. Okay? But remember that then, like later when I was asking you to work problems, you were struggling to write out all the steps because you'd never really written them before until you were on your own. So if you're copying examples, writing them down, you're training your brain to know what to write. And that's why we do examples. So that's why notes can be helpful. Not just as something to refer back to, but as a process of writing. Okay? So this is between, so that's limits on using average rate of change for a given point, okay? So now we're going to extend this to generate a, what is called a derivative. And a derivative is a function where, so far, okay, if I said to you, if I gave you s equals t squared, like we've been using, and I said to you, find the slope at 1, you'd have to do the limit as t approaches 1 and write it out, right, with the definition of slope and all that kind of stuff. And then I said, now give me the slope at 5. To go through the whole process again, right? So let's generalize that. So we're going to write a function. So if I have f of x, okay, this is going to be called f prime of x, and it's a function that goes along with f of x that I plug in x and it spits out the slope at that point. Okay, cool. Sounds cool, right? All right. Is this like, are your head swimming or are you good?
Sound good.
Okay, cool. Alright. So, yada yada. Okay? So let's say this. Average rate of change for y equals f of x. If y equals f of x. Okay? Our generalized delta y over delta x would be, let's imagine it's between on the interval a to b. Okay? A to b. So b is further along than a. So we would go f of b minus f of a over b minus a. Right? I would do change in y over change in x. That's what it would be for me. Okay? And they say there, they remind us there, that geometrically, this would be the slope of a secant line. So remember, tangent touches a curve at a single point. Secant crosses the curve at 2 points and goes inside of it. Yes? Remember this from geometry?
Yeah.
So this is the slope of a secant line right here. But where at A, f of A, and B, f of B. This is all on page 74. Right? So now we'll say this, though. The derivative of the function f at x equals a, denoted by f prime of a, and read f prime of a, how I just read it, is, okay, f prime of a equals the limit as x goes to a, so this is what we were just doing, as x goes to a, of f of x minus f of a over x minus a. Okay? So again, as x goes to a, this is going to go to 0. So that's why we have to use a limit, because we don't really ever want x to get to a, because then we'd be divided by 0, and that's illegal. So rather, we're just going to say, what happens as x gets very, very, very close to a? What do I get very, very close to in y? Okay? Or in the slope. So that's that geometrically the slope. This is the slope of the tangent line at A. Okay, so this is what we've covered. Now we can also write it this way. Yep. F prime of A equals limit as h approaches 0. So where h is just the difference between x and a. Of f of a plus h minus f of a over h. And that's how I was talking about writing it this way earlier, right? Where basically we just isolate the difference between the point we're looking for and these points we're making up, and we say, so this is going, there's some point that is h further along than a, and so that difference between a and that point is what I'm dividing by, okay? So those are all three kind of the same thing, okay? But this is what you're going to use most for a derivative moving forward, the one with h. Because as they note there on the page, it's more computationally useful. And we'll use it here in just a moment. Okay? So let me rewrite that one over here. F prime of a, again, the f prime function gives me the slope at a given, when x equals a, along the curve f of x. Okay? Equals the limits as h goes to 0 of f of a plus h minus f of a over h. All right. So check this out. It says, find f prime of 4. Find f prime of 4 if f of x equals 2x squared minus 3. Okay? All right. So we want to use this definition. Okay? So we're going to go, all right, f prime of 4. I'm looking for, so I would say f prime of 4 equals the limit as h goes to 0 of, now, right now I'm just going to write f of 4 plus h, okay, minus f of 4 over h, okay? Yep. Yep. Now I'm going to write equals limit as h goes to 0 of 2 times 4 plus h squared minus 3, okay, minus 2x squared minus 3 all over h, okay, equals the limits as h goes to 0. So the game is, so what's causing the problem which causes me to have to use a limit? As I begin to explain this, I want to point something out.
If you don't want your denominator to be 0.
You don't want your denominator to be 0. So here's what we're ultimately going to be looking for, is to cancel this h with the top, so that there's nothing in the denominator anymore. Okay? So limit as h goes to 0 of 2 times 16 plus 8, 16 plus 8h plus h squared minus 3 minus 2x squared plus 3. I just distributed the negative all over h equals limit as h goes to 0 of, now, 32 plus 8h plus h squared minus 3. So distributed the 2. So that now that I've done all my multiplication, everything's just being added and subtracted, so I'm not worrying about these parentheses anymore. Minus 2x squared plus 3 all over h equals the limit as h goes to 0 of, sorry, I said 2x squared. This should have been 4. So now it's going to be 16 times 2 is 32. Okay. Okay. So 32 minus 32, those are going to cancel. Yeah. Okay, I'm ending up with, and then 3 and minus 3 cancel. So I end up with h squared plus 8h over h. Nope, sorry. Two times 16 is 32. 2 times 8 is 16. 2 times h squared is 2h squared. There you go. Sorry about that. So now it's 2h squared plus 16h over h equals the limit as h goes to 0 of 2h plus 16. Okay? So what is the limit as h goes to 0 of 2h plus 16?
16.
16. So the slope of the tangent line of f of x at 4 is 16. Now, just so you know, as you progress in calculus, there's going to be a much easier way to do this. Okay? Much more direct. But for now, you have to understand this, so we do it. Okay? So this is what we call the derivative, and they write the definition one last time at the bottom of 741. Okay? Where they write f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. So notice writing it this way is the derivative at a point where x equals a. The other one where they just say f prime of x, that's defining it for all x, okay, for any point. So we can write the same thing of f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. Okay, and so then that's for. So this was just defined as being at a point. This is defined as being everywhere. So that's where I was saying it's a function that goes alongside f of x. And I said, I want to say it's parallel, but it's not. Like parallel is a geometric term, so it just goes with they go together. Okay? It's a derivative of, literally a derivative of. So, cool. So then on 742, you have example 5, where finally now we're doing the same thing, but they're saying finding the derivative of a function. So now, rather than using specific numbers, we're just going to simplify the expression, okay? Simplify this expression using a particular f of x. Let's check that out. So it says, it has an a and a b, and they introduce two kinds of notation, where we can also call, instead of f prime of x, we can say dy dx. Dy dx. Okay? Dy dx. They introduced there that's called Leibniz notation, because a guy named Leibniz did it. Later on, way later on in mathematics, you will actually begin, this can be helpful because you can actually split these up. Right now, don't worry about that. Okay? Just understand that they get written this way, but it can be helpful later on in differential equations to split these up. Okay? So the derivative, it says find f prime of x if f of x equals x squared. F of x, yeah. Find f prime of x if f of x equals x squared. Okay? So we go, well, f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h, which is x plus h minus x. Okay? That equals the limit as h goes to 0 of x plus h squared minus x squared over h. X squared plus 2xh plus h squared minus x squared over h. Of x squared minus x squared, those cancel. So I'm left with 2xh plus h squared over h. Okay. So limit as h goes to 0 of h times 2x plus h over h equals the limit as h goes to 0 of 2x plus h. So Nick, what is the limit as h goes to 0 of 2x plus h?
If h is 0, then it's 2x.
Exactly. Boom. So this is the function that spits out the slope of the tangent line to the curve at a given x. So for the parabola, the parent parabola, you can find the slope of any tangent line that touches the parabola by just plugging it, by doubling the x. Okay? Cool? Cool. Great. This next was a little more complicated. Okay. Oh, because it's 1 on x, that's why. All right. So now it says, find dy dx if, what does it say, y equals? Yeah, y equals 1 on x. So typically, if we're saying dy dx, it's going to write it in y equals notation. If it's saying f prime, it's going to write it in f of notation. Okay? So, dy dx equals the limit as h goes to 0 of, now, we can go ahead and, we're going to go ahead and use the f of notation here for the definition. F of x plus h minus f of x over h equals the limit as h goes to 0 of 1 over x plus h minus 1 over x all over h over 1. So once I have a fraction in the numerator, I like to have a fraction in the denominator or vice versa. So I just wrote h over 1. Limit as h approaches 0 of, so in order to add those, I have to, so like, it's going to be x minus x plus h, right? So x minus x plus h all over x times x plus h all over h over 1 equals the limit as h goes to 0 of, now, x minus x cancels. This negative applies to that h though, so I have negative h over x squared plus xh all over h over 1. You know what they did in the book? They never actually did this multiplication, so I won't either. X times x plus h. Okay? That's an h on n. So that equals the limit as h goes to 0. Now, I can do outers over inners. Also, I can just cancel these. So I can cancel numerators or cancel denominators. You would see that when I do my outers over inners. This would be the numerator. This would be the denominator. So I'd have an h in the numerator and an h in the denominator, right? So I'm just going to go ahead and cancel those now. So this is just negative 1 now. Okay? So now I have negative 1 over the denominator of x times x plus h. Okay? So I still have a problem. Right? No, I don't. No, I don't. Yeah, see, I should distribute that x. Do they ever distribute the x? They don't. They just go ahead and do it now. So, so what is the limit as h goes to 0 of negative 1 over x times x plus h?
Minus 1 over x squared.
Negative 1 over x squared. Because this h goes to 0, which makes this quantity just x. So x times x is x squared. So the function of x that spits out the slope of the tangent line for this curve at a given x is negative 1 over x squared. Okay? Cool. Any questions? Would you like me to show you how this gets simpler?
Sure.
Just as a little bonus. Okay. Imagine that I have this. Fx equals x squared. F prime of x equals 2x. Okay, so that's clear. But then if I'm going to go ahead and write this as f of x equals. So if I had to write this with using an exponent instead of a fraction, what would it be?
It'd be x to the negative 1.
And then if I had to write this using an exponent, what would it be?
X to the negative 2. No,
Negative
1
x to the negative 2.
Oh, x to the... Okay.
So negative x to the negative 2. You see that? Okay? Because there's this negative out front, but there's also an exponent in the denominator. Negative out front is still out front. The exponent in the denominator makes the exponent negative. Okay? So look at from here to here, and from here to here, what happened?
Well, it went up an x, like up a power.
From where to where?
From x negative 1 to...
So did it go up a power or down a power?
Oh, it went down.
Down a power. What happened here?
It got rid of the exponent and it was multiplying by 2 instead of
Okay, so
multiplying by
here,
itself.
look, here you said it went down a power. Here you said it got rid of the exponent. Why did you use differently? So did it also go down a power here?
Yes.
From 2 to 1. From negative 1 to negative 2. Tell me about where these coefficients came from. That's a 1. A dotted 1.
I get it.
So there's a negative 1 here. Is there a negative 1 here? There's a 2 here.
So
Is there a 2 here?
You're moving it from there to the front.
And then dropping the exponent by 1. So you take the exponent down in front, and then drop the exponent by 1. This is what you'll unpack in calculus. But this is how now, if it's a polynomial, you can still find the derivative very quickly. Every time there's an exponent, you drop it in front and subtract 1. Drop it in front and subtract 1. Drop it in front and subtract 1. And that's why the constant terms go away. Well, why the constant terms go away is because the math we did. In our shorthand version, the constant terms go away because they start with an exponent of 1, or of 0, so they're just gone. Cool? Anyways, that's bonus content that you'll get later. But just hope for you that you don't have to do longhand limits every time.